Welcome to the ePathshala lecture series in computer science. We are looking at the computer architecture course. So this module is to discuss about warehouse scale computers. So the learning objectives are to discuss about the features of warehouse scale computers and to discuss how request level parallelism is exploited here. So if you look at the various classes of parallelism and parallel architectures, there are basically two types of parallelism present in applications. One is data level parallelism, as there are many data items that can be operated in parallel. The other one is task level parallelism, which basically arises because tasks of work are created and these can be operated independently and in parallel. And given these two types of parallelism that are exhibited by applications, computer hardware tries to exploit these parallelism. So computer hardware exploits the data level parallelism and thread level parallelism in four major ways. ILP exploits DLP at modest levels using the help of compilers with ideas like pipelining and speculative execution. So even if you look at instruction level parallelism, we try to exploit data level parallelism to some extent because we do pipelining and speculative execution and all that. And also when you look at vector architectures and GPUs, which we discussed in an earlier module, they definitely try to exploit the data level parallelism. And when you look at thread level parallelism, which is exploited, we even had an example of a Niagara processor where there is extensive thread level support. Thread level parallelism exploits either the data level parallelism or the task level parallelism in a tightly coupled hardware model that allows for interaction among threads. And request level parallelism basically exploits parallelism among largely decoupled tasks which are specified by the programmer or the OS. Examples are when you have multiple requests coming in, when you have a server which has to cater to multiple transactions or there are multiple requests coming in, what is more predominantly available, what type of parallelism that is predominantly available is request level parallelism. So now we look at a completely different style of architecture, a warehouse scale computer, which is used to exploit the request level parallelism. Basically, when you look at warehouse scale computers form the foundation of all internet services. You know how internet services have become very essential these days. All of us do a lot of search, we are on social networks, we try to access online maps, we do a lot of video sharing, we do a lot of online mapping, shopping, we do emails, we use clouds for storage as well as other services of the cloud. So for all this, internet becomes essential, and the foundation of internet services is what is your warehouse scale computer. And the architecture and the operation of the warehouse scale computer are definitely different from that of data centers. So it is once you know that internet services are becoming essential and have become essential already, and you know the foundation of internet services is warehouse scale computers, it becomes a necessity for us to look into warehouse scale computers. Warehouse scale computers basically are descendants of the supercomputer. So earlier supercomputers were basically brought in because they had to do some niche processing. You have some specific data crunching operations, scientific computing that had to be carried out on supercomputers. So this is actually a modest descendant of the supercomputer, but not to carry out specialized operations pertaining to a specific group of people. It is more to provide information technology to the world rather than high performance computing to a small group of scientists and engineers. So the order of magnitude of users of internet services and hence warehouse scale computers is definitely much more than users of high performance computing. So to give you a feel of what a warehouse scale computer is, this tells you the type of computers you have. You have more than 100K servers available in one warehouse scale computer, 100K servers available. The cost is about more than $150 million. You have requests from millions of users coming in like Google, Facebook, etc. And you know, cloud computing is a model, it's a utility model where users can rent, compute and store within a warehouse scale computer. and with an of course associated service level agreement. So, the cloud computing, which is utility computing, has basically become possible because of your warehouse scale computers. So, if you look at the goals and requirements of warehouse scale computers, the architects of warehouse scale computers as well as the architects of servers, you have a number of design factors which is common for these architects. One is cost performance ratio. See, in both cases, both in servers as well as WSCs, warehouse scale computers, the cost performance ratio becomes very important. For example, when you look at warehouse scale computers, because of the volumes of scale involved, you have I said 100K, 50,000 to 100K servers available in one place. So, even if you make a small saving, you know that you are going to save a lot. There is a lot of saving that occurs. So, cost performance ratio becomes very important when you look at both WSCs as well as servers. The second one is energy efficiency. So, when you look at a warehouse scale computer which is going to house 100K servers, 50,000 to 100K servers, you know you need to have an infrastructure and you need to have power distribution and cooling facilities to handle this massive number of computers. So, obviously, you will have to worry about energy efficiency because the energy consumed will have to be proportional to the amount of power that you get and how it gets distributed. And because the power distribution and cooling plays a major role as far as the cost of a WSC is concerned, you will definitely have to look at conserving power. So, energy becomes very important and work per joule becomes very important. The third factor is dependability via redundancy. Dependability becomes a very, very important problem both when you look at WSCs as well as servers. Normally, when you look at a server, you try to look at going in for high-end servers, you pay a lot of money there and you try to provide dependability there by way of going in for good hardware. Whereas when you look at servers, because of the volumes involved, when you look at 50,000 to 100K servers available there, machines available there, you definitely can't assume that these machines will not fail. So, you do not have to really spend money on getting specialized architectures and all that. Dependability is basically provided by means of redundancy. So, it is enough if you have normal servers that are available, you can have extensive networking, and dependability is basically provided by means of redundancy. And looking at the number of machines that are available, obviously all of them will have to be connected by means of a network. So, the network I/O also becomes very, very important. When you look at the WSC goals and requirements and the important design factors for WSCs and servers, there are many common factors between WSCs and servers. The first one is the cost performance ratio. So, in both cases, the cost per performance becomes very important, particularly when you look at WSCs. Because of the volumes involved, you have 50,000 to 100K servers which are involved, and even if you make, and there is a lot of money involved. So, even if you have a say 5% saving or 10% saving happening, that reflects a lot on the money saved. So, the cost performance becomes very important when you look at WSCs and servers. The second factor is energy efficiency. Again, when you look at a WSC and the infrastructure required for a WSC which houses so many number of servers, basically what happens is a lot of money is spent on the power distribution and cooling, and this power that is received should also be proportional to the power that is consumed. So, if you try to reduce your power consumed, you are going to have saving on the power that is distributed also and the cooling. So, we would definitely have to look at energy efficiency, and work per joule definitely matters. The third one is dependability via redundancy. Normally, dependability is achieved through redundancy. In some cases, when you look at specialized servers, you try to look at increasing the dependability, going in for expensive components which will not fail so easily. But in the case of a WSC, with so many machines coming into picture, so many computing nodes coming into picture, you do not have to go in for specialized architectures. You just have normal machines connected by means of a network, and dependency is basically achieved via redundancy. Redundancy is the main concept that is used for dependability. Network I/O again becomes very essential, because with so many machines available, all of them will have to be interconnected. All of them are interconnected by means of extensive networking. And the last factor is, of course, you will have both interactive workloads as well as batch processing workloads. When you are trying to do an online reservation, or you are trying to do online shopping, you have a number of interactive workloads coming in. But at the same time, you may also have to do a lot of batch processing operations. For example, you have a web crawler available in the background. It has crawled and given you a lot of pages. You will have to index all of them. So, all that will happen offline as a batch processing workload. So, you should be able to cater to both interactive workloads as well as batch processing workloads. So, these are some of the commonalities. And apart from the common requirements, you also have some characteristics that are different for WSEs and servers. In the case of WSE, your ample computational parallelism is not important, because you know that there are a number of jobs which are totally independent. So, request level parallelism is already there. You do not have to worry about having parallelism, computational parallelism in the applications that you are looking at. Whereas, when you are looking at servers, you will have to worry about parallelism available in your application and try to look at how to exploit this parallelism. In the case of WSEs, it automatically comes in because most of the jobs are totally independent, and you anyway have request level parallelism explicitly available in them. And if you look at the operational cost count between a WSE and a server, power consumption is a primary, not secondary constraint while designing the WSE system as against your servers. And last of all, the scale. If you are looking at the scale or the volumes that are involved in a WSE, because of the scale, you have both opportunities as well as problems. Because you are looking about 50,000 to 100,000 servers, and you are trying to house all of them together, the volumes itself will give you a lot of discounts, and there is an economy of scale. Because you buy in huge volumes, you are definitely going to have discounts, and that gives you an economy of scale. At the same time, you also have a flip side to it. When you have so many machines put together in one place with so many storages available and all that, you definitely will have failures. You can't say that it will not have any failures. You will have failures, and you should be able to handle this failure, and you should be able to provide almost 100% availability in a warehouse scale computer. And all this is normally handled by means of redundancy. And if you look at the differences with HPC clusters, high performance computing clusters, clusters normally have higher performance processors and networks. Clusters emphasize thread level parallelism, whereas WSEs emphasize request level parallelism. And if you look at differences with data centers, so though many people say that WSEs are big data centers, you definitely have differences with data centers. Data centers basically consolidate different machines and different software into one location which people can use. Data centers emphasize virtual machines and hardware heterogeneity in order to serve varied types of customers, whereas a WSE is not like that. So, having seen a basic requirement of WSEs, what is the programming model that is used and what types of workloads do you have there? So, as I already mentioned, you have both batch processing workloads coming in as well as interactive workloads coming in. So, when you are looking at the batch processing framework, the most popular framework that is used is the MapReduce framework and its open source twin, which is the Hadoop. So, the MapReduce framework is very popular, and what the map process does is it just applies a programmer supplied function to each logical input record, and the map process itself will run on thousands of computers. So, the same thing, if you look at a data set, for example, the data set will be distributed among thousands of computers. You have a map process running on each one of them. So, what map process is done is dependent upon what you want to do. It is a programmer supplied function. So, each mapper will perform a mapping operation on this data that is given to it, and it will produce a new set of key value pairs as intermediate values. Each one of them writes onto an intermediate file which has to go to a reducer. So, the input is converted to a key value pair by the mapping process, and the reducer basically collapses, takes in these key value pairs and collapses values using another programmer supplied function. So, reducers also can be many. So, the reducers will take in the information that is given by each one of these mappers. It depends on which mapper is going to supply which reducer. All that is decided by means of a master controller. So, the reducer will take in each of these reducers will take in the key value pairs. They will do a consolidation operation or a collapsing operation, and what operation is performed is again dependent on the programmer supplied function. So, to give you an example, suppose if you have to count the number of occurrences of a particular key value in a string. So, the map process, what it does is, the information that is given to us is the document name and the document contents, and for each word that is available in the document, it just emits a key value pair. So, the key is your the data word. So, the document is split into each word separately. So, the key value is your word, and the value is, because it is present there, it puts a 1 there. So, you have, suppose if you look at a word like string, for example, string occurs in multiple places. So, it will say string 1, string 1, string 1. So, all this is produced by means of the map process, and you may have multiple such mappers. So, each one of these mappers will identify each one of these key values. So, each one of these keys, and it will associate a value with it as 1. Now, what the reducer does is, it takes all these key value pairs and it basically has to count the number of occurrences of a particular word. For example, if string is your key here, it will try to identify all the key value pairs which has a key value of string, and it will say, it will aggregate all of them. So, it will say string 1 1 1. So, finally, suppose if it occurs 3 times, then it will aggregate it and say string occurs 3 times. So, that is the reducer's job. Now, this mapping process can happen on one document. One document can be split into multiple parts, or you may have multiple documents given to each of these mappers. So, finally, the reducer takes input from each of these mapper processes. It takes in the key value pair, aggregates all of them and produces the result. So, this is basically what happens when in a MapReduce framework, and this is the most common programming model that is used in a WSC. So, MapReduce is basically a generalization of your SIMD, because you are basically trying to exploit the data level parallelism. It may not be data level parallelism like how we have looked at data level parallelism that is available among the data elements available in memory. It is more of, it may be in terms of documents, it may be in terms of files that you are looking at, whatever it is. And you basically pass functions to the map and reduce jobs. So, the same functions are passed on to the various map and reduce jobs, and you are trying to look at exploiting the data level parallelism among these various functions, because the same function is executed on the various map processes and various reduce processes. It also accommodates variability in performance. So, if you look at a warehouse-scale computer, what you will have to worry about the workloads is, it is not that you are going to have the same workload given to a WSC at all points of time. Say for example, if you take an Amazon online shopping, you know that Amazon or any of these online shoppers give you a lot of discounts during special occasions, a Diwali or a New Year sale. You know they offer a lot of discounts, and obviously there is going to be a lot of sales happening at that point. And there are certain points of time when the sale is not going to be too high. So, you are going to have variability in the demands that come in, and because of this variability in demands that are coming in, you will also have to accommodate this variability when you are designing the systems. And you will also have to worry about another factor, variability in performance of the individual machines. So, individual machine, I may have a fast machine which does the map process or reduce process very fast. You also may have a machine which may take a lot of time to execute. So, how do you accommodate this variability in performance? So, variability in performance, variability in the types of workloads that are coming up. So, you will have to handle both. So, variability in performance, you may have to do backup execution for unfinished jobs. Suppose you've distributed the job to 10 mappers and 7 of them have finished, 3 mapper processes have not yet finished. So, you can either wait for them to finish, or these unfinished jobs, if you know that they can be executed at a faster rate at some other mapper which has already finished job, you can also transfer the complete job to the other mapper process and get it executed. So, you should be able to accommodate variability in performance. The other issue is of course overcoming failures. Overcoming failures, I have already told you that you use replicas of data across different servers. So, you do not have the same data available only in one place. The data gets replicated in multiple places. So, that is how you basically take care of failures. So, even if there is failure happening in one place, you know the other two are anyway there. So, you can just take the data from those servers. And also make sure that when you look at the hardware level, we will see how you have a number of racks and you have arrays of racks and all that. So, the place in which this data is also distributed also has an important role to play. Suppose if you put everything within the same array, and if that array fails, you have a problem. So, where this data is available, how it gets replicated, all that has to be decided properly so that you are able to overcome failures. And again, if you have a failed thread of execution, suppose some server has failed, how do you detect the failed thread of execution and how do you restart threads? So, normally we assume that if something fails, you do not start from that point of execution, because in that case you do not know how much has been finished, whether there is going to be a replication of the work that has been done and all that. So, once you find that something has failed, you just leave it at that and start the job all over again for the failed thread. And it is also that you will have to look at use of MR within the MapReduce framework within Google, just to give you a feel of how much this MapReduce framework has gained popularity. So, if you look at Google, within Google the MapReduce framework has been growing every year, and within a short span of time you find that the number of MR jobs has increased 100x times. Data being processed has again increased 100 times, and the number of servers per job has increased 3 times. So, that tells you how the MapReduce framework has become very, very popular with WSEs. MapReduce runtime environment schedules the map and reduce tasks to the WSE nodes. And the other thing that is very important is availability. And in order to handle the availability feature, we have already seen that you use replicas of data across different servers, and you do not have to go in for a very strict consistency model. We have already looked at the consistency models. So, the moment you have replicas of data across different servers, you need to have consistency among them. So, you try to look at not a very rigid consistency model, you try to go in for a relaxed consistency model, because you know that you do not have to have all the replicas agreeing all the time. Ultimately, at some point of time, eventually they should agree. So, you do not have to worry too much about a strict consistency model. You can look at relaxed consistency model. As I already mentioned, workload demands. The workloads also can vary considerably depending upon the period of the year, time of the day, whatever it is. So, you should be able to also accommodate these variation in the workload demands, and the hardware as well as the software should take note of the varying loads. So, if you look at the architecture of WSE, WSE often uses a hierarchy of networks for interconnection. Because of the volumes of the number of nodes that are involved, you definitely have to have extensive network connecting all of them. So, you normally look at a hierarchy of networks for interconnection. So, you look at racks and then you look at array of racks. So, you have a rack switch, you have an array switch, and all of them connected by means of interconnect. So, you have each 19-inch rack holds 48 1U servers connected to a rack switch, and the rack switches are uplink to switch higher in the hierarchy. So, the uplink has 48 by n times lower bandwidth, where n is the number of uplink ports. This is an oversubscription of course, and the goal is to maximize locality of communication relative to the rack. And storage, again you have different storage options. You can either use disks inside the servers, or you can try to look at network attached storage through InfiniBand, but generally WSEs rely on local disks, and GFS, the Google file system, uses local disks and maintains at least 3 replicas for availability purposes. And then for each array of racks, you have an array switch. This switch connects an array of racks. The array switch should have 10x the bisection bandwidth of the rack switch. The cost of n port switch grows as n squared. It often utilizes the content addressable memory chips and FPGAs. So this gives you an example of the latency involved in accessing data if it is available in the local disk, if it is available within the same rack, or it is available within the same array of racks. That gives you a feel of the latency that is involved. So if you look at the WSE memory hierarchy, a rack can hold multiple servers, and you have a rack switch that is used for communication within and out of the rack, and then an array switch which connects array of racks, and the latency grows if data is fetched from a remote DRAM or disk. Bandwidth within a rack is much higher than between the arrays, and hence software must be aware of this data placement in order to reduce the latency. The other important factor that you will have to look at when you are looking at WSE is the infrastructure costs. So when you are looking at infrastructure, the location of WSE becomes important. So you will have to have proximity to internet backbones, you will have to take care of the electricity cost, the property rate tax rates, you will have to make sure that the place that you are identifying for the WSE should have low risk from earthquakes, floods and hurricanes. So all that becomes important when you are looking at the location of a WSE. And similarly, when you are looking at power distribution, because there is an enormous requirement for power, and power is very expensive, and it gets distributed through multiple stages, through multiple components, power distribution becomes very, very critical, and it forms a major part of the cost. So to give you a feel of what happens in power distribution, you see that power is distributed through multiple points. It goes through 4 or 5 stages before it finally reaches the server that you are looking at. There is a loss happening at each one of these stages. You will have to make sure that losses are getting reduced at each of these points, and whatever can be done to reduce these losses, you will find that there is a saving that matters in the case of your infrastructure cost. And the other important factor is cooling. So in order to avoid the cost involved with cooling, you normally have again different techniques that are used for reducing the costs associated with your cooling. One technique is you try to maintain the rooms not at very low temperatures, but you maintain it between say 64 degree Fahrenheit and 71 degree Fahrenheit. You can also look at using cooling towers, and the minimum temperature is the wet bulb temperature. So this gives you a feel of what types of cooling that happens in a WSE. So the major infrastructure cost not only is the building cost, it is basically goes into the power distribution cost and the cooling cost. And cooling system also uses water. For example, the consumption is about 70,000 to 200,000 gallons per day for an 8 megawatt facility. And if you look at the power cost breakdown, chillers 30 to 50% of the power used by the IT equipment, and air conditioning uses about 10 to 20% of the IT power, mostly due to fans. So all this gives you an idea of how much of money has to be invested into your power and the power requirements and the cooling requirements. So in order to measure the efficiency of a WSE, we normally use a term which is called the power utilization effectiveness, or PEU, which is defined as the total facility power divided by the IT equipment power. This obviously is greater than 1, because you know that lot of money goes in, lot of power goes into creating the facility rather than supplying it to the servers. This obviously is greater than 1. It ranges from 1.33 to 3.33. A study that has been done indicates that the median is normally 1.69. And as far as performance is concerned, latency is an important metric because it is seen by users. So the user puts in a request, and if the user does not get a response immediately, the number of requests that he puts in obviously comes down. So, latency is an important metric. A Bing study was conducted which shows that users will use the search less as the response time increases. And of course, in order to make sure that latency is taken care of, you have various service level objectives. For example, you can't say you make sure that 99% of the requests will have to fall below or take a latency of less than 100 milliseconds. So, if you look at a cost of a WSC, there are basically two components that contribute to the cost of a WSC. One is the capital expenditure CapEx, which is the cost to build a WSC. CapEx can be amortized into a monthly estimate by assuming that the facilities will last for say 10 years, server parts will last for 3 years, and networking parts will last 4 years. The second one is your day-to-day expenses in terms of operational expenditure. So, this is basically the cost to operate a WSC, say the monthly bill for energy failures, personnel, etc. And improving energy efficiency, you know, an uploaded server dissipates a large amount of power. So, ideally we want energy proportional computing, but in reality servers, you know, are not energy proportional. So, you can approach energy proportionality by turning on a few servers that are heavily utilized. You can also look at other metrics. Performance does matter, as I already pointed out, especially latency. So, I have already given you this case study. And reliability and availability are very, very important given the large scale of WSCs. So, even a server with an MTTF of 25 years with 50K servers, you know, it will lead to about 5 server failures a day. Similarly, the annual disk failure rate is 2 to 10%, which means there will be one disk failure happening every hour. So, you cannot avoid these failures because of the volumes involved. You will have to take care of it only by redundancy. So, to summarize what we did in this module, we've seen that warehouse scale computers form the basis of internet usage and have gained popularity. So, it is only right that we look at the architecture of warehouse scale computers. These WSCs share some commonalities with servers, yet are different in some ways. The important design factors to be considered in the case of a WSC are the cost performance ratio, the energy efficiency, how dependability is provided via redundancy, what type of network I/O are you going to provide, and handling of both interactive as well as batch processing workloads. And infrastructure costs form an important part of the cost, and you know that the way you can measure the efficiency of a WSC is through your power utilization effectiveness, which is an important measure. These are the references. Thank you.